Good afternoon. Who's here? I see a couple of people are watching already. As explained in the description, I'm going to discuss yesterday's quiz and then get back into the sampling distribution of a statistic Unit 5 material, and we'll do some problems there. So for today's class, you should have watched the videos that are provided with a link on the Moodle site, in the classroom site. V60, 61, V62, all the way to V65. Oh, I think it's actually V66. V66, I have to fix that. I'm just going to wait to see who else comes in. Natalia's here. All right, so the quiz was not done too well, by and large. I think less than half of you got it right. But that means, as usual, for the quizzes, they're not difficult problems, but they are, they're conceptual. Maybe I've talked around the issue, but not put it in these terms. That's how the quizzes are. It's not a replication. I'm not getting you just to replicate what I've taught you. I'm asking you to take it by, in a synthesized way with the information that you've learned. How would you approach this problem? So the best thing to do on quizzes is to explain to me your thinking, so then I can give you some credit that way. And I gave you an opportunity with this quiz. I did ask you at the top, the overall question is, which of the variables defined below has a binomial distribution? Circle the best alternative. And I call that number 1. I guess you should think that's question number 1. And the second question, define what a success is in the option you selected, and also indicate what N and P are in the option that you select. If P isn't given precisely, or you can't compute it by the information given, however it's known, just write P. All right, so what you could do is go through each one. Well, that's what I'm going to do now. I'm going to go through each one and tell you why they aren't the right answer, and then I'll explain why. By the time we get to it, you get the feel of why the answer is the correct answer. So let's see, the first scenario. Make it a bit bigger. Okay. A 911 operator works one day from 9 a.m. until 5 p.m. The probability of a call is known. Define X as the number of calls received by the operator during her shift. So let's start these problems as we did when I was trying to identify if I had a binomial setting so that I could solve the problems in the homework. What I did was I told you look for the parameters, and in P try and define success. And so I began with a listing of X and P and K, right? So there's your list for you to think of. I already give you X here in each one I do, so that's done for you. From here you can extract what a success is, or what they're attempting, anyway, how you could possibly frame this as a binomial. X is the number of calls received by the operator during her shift. So we have to get from that success and the number of trials. Success is a call received, I guess, could say that, by the operator during her shift. Now, usually for a binomial, the statement is of the form x equals number of successes in n independent trials. So that's what x is. Usually that's how we frame the binomial variable. So what you need to do is identify the success and what's the n. How many times did they attempt to look for the success? In this problem, the success, the thing you're looking for, is counting calls received. Okay, so there's some notion of success there. But n independent trials, we have a problem with n here because it's saying during her shift. So it's vague if we're going to refer to that as are we going to check every hour? Are we going to check every minute? Are we going to check over the full span of her shift? It's not clear how many times we're looking. It's just not clear. So in this case, we sort of have a p. Well, they say the probability is known, so we have a p. You could say that would be the p. We'll say, oops, I pressed the wrong. So call received by the operator could be the success. And then as far as the n independent trials, that's the problem. So it looks like we have the success here. But there's no clear n. So that's the problem there, right? So that one is not the answer. A is not correct. What about B? So thinking along the same lines, one moment. Thinking along the same lines. An airplane carrying 100 passengers has 2 emergency exits. One at the front of the plane and one at the back. The airplane makes an emergency landing and people exit through the door that is closest to them. The number of people who leave the plane through the front exit is Rx. All right, so we see there's 100 passengers. So we're gonna observe 100 passengers. We can tag that on at the end. So I'm gonna keep all the stuff about n in blue and information about p in red. So x number of people who leave the plane through the front exits, you can add out of 100 because there's 100 people. So I'll take this as the n. So n equals 100. What about the p? So p should be, let's put that in red, the number of people who leave the plane through the front exit. So that's leaving the plane through the front exit is a success. That's what we're looking for. So that's going to be the success. What's the probability of leaving the plane through the front exit? Now, they don't say what it is, but in fact, when you think about it, the p would be different for people who are closer to the front exit than people who are further away from the front exit, right? The people closer to the front exit would probably be more likely to exit through the front exit, and the people further away would probably exit through the back exit. So the way it's laid out, The success is front exit and the failure is back exit. We don't have the probabilities for this. In fact, thinking a little more, the P is not going to be a constant. It's not going to be the same for every person. So P is the problem here. We don't know what the P is, what's one side, but the P keeps changing for each person that you consider when you observe which way they went out of the plane. All right, so that's the problem for B. Any questions so far? C is the right answer. C is the right answer. C is binomial. Let's see why. Take a simple random sample of 25 Puerto Ricans. So that's our N. We're going to take a sample. So N is equal to 25. It's pretty clear. The probability of having a particular blood type is known. Okay, so it looks like from the next statement, the number of people in a sample with blood type A. Blood type A is the success. Failure is the other set of blood types. And the probability of success, P, is known. So that's what you had to say. P is known. It's the same for every person that you look at. I mean, given before you know who they are, as each person enters without knowing who they are, the chance that they have that blood type is the same. Okay? So that is a binomial. So this is the correct answer. B is not the correct answer. C is the correct answer. All right? Very good. Some of you got that. Let's see D. Why is D not the right answer? What's wrong with D? You randomly select 5 cards from a standard deck of cards, which contains 13 hearts, 13 diamonds, 13 clubs, and 13 spades. X is the number of diamonds. All right, so now we get the hang of this. So first of all, let's tag on the ending, because we're used to calling a success. We're used to stating that the binomial is the number of successes in n independent trials. I'll move this up a bit so you can see what I wrote there. So I'm going to tag on here, selected out of 5. So it's 5 independent trials. That's the N. All right. And then what would be the P? The P in this case is the problem, because every time I select a card from the deck, a deck of 52 cards, each time I pick a card, whatever it is, I'm changing the chance that there's a diamond in the remaining deck. So because I keep changing the probability of picking a diamond, the P is not known. Okay, so the P is not clear. It needs to be known in advance, and it needs to be the same for each trial. So D is not the right answer. I want to move this down. So D is not the right answer either. And finally, you repeatedly toss a pair of fair dice. You toss a pair of fair dice and you look for the number of tosses required to obtain a sum of 7 for the first time. So what are we doing? Let's look at that statement. Let's begin with the statement and see if it's complete. Is it saying the number of successes in n independent trials? Number of tosses required to obtain a sum of 7 for the first time. Aha, so I can't even tag on out of at the end. It's very confusing. So there's no n. There's no defined fixed n. All right, I'm going to toss until I get what I'm looking for. That's not a binomial setting. All right, so even though I'm looking for a 7, that would be my success. And I could compute that P could be computed. The problem is I haven't specified in advance how many times I'm tossing. In fact, this variable is defined by the number of tosses until I get what I'm looking for. It's not a binomial setting. All right? So I presented, okay, so this is wrong. The answer is C. I presented in the notes the variables that are Poisson and hypergeometric. Just to give you an idea, a taste of other distributions, and I'm not going to test you on those in the final exam, but I put some information on there, and in fact, these ones that are wrong, like D and E, they'd fit better in the hypergeometric or the Poisson. I think the D is hypergeometric and E is a Poisson distribution. That's not, when I talk about binomial, which is the one I want you to know, sometimes it's good to know what it's not so that you can discern when you read problems that clearly that's not a binomial, it's something else. It would be nice if you could learn those, but I know time is tight, and we're going to focus on the binomial in this course. All right, any questions about that? Any issues? So most people did it wrong, but some people got it right. Will you have a chance to rewrite the quizzes? Yes, I will give you the opportunity. So next Thursday, I will post quiz for SDS. I'll post a quiz for BIN, and I'll post a quiz for the Bayes problem that I gave you, for probability. Anyway, maybe 2 problems, one with Bayes and one with something else. Okay? So that way you have a chance to rewrite, and I'll give you the 3 hours to work on those problems. And the only thing I ask is that you work independently. I know it's tempting to communicate with your classmates, but if you really want a sense of statistics, you're going to have to battle through on your own so you can carry that knowledge away. And it's your own knowledge. Okay, you guys can share, you guys can work on things together. There's a ton of problems to work on together if you want. Don't just wait for the quiz problems. They certainly are not enough to prepare for the final exam. All right, so I'm going to get back to where we left off. Well, I'm actually going to go a little bit ahead of that. I asked you to watch the videos for these pages. So all the material in between is several exercises for you to do. I provided videos for pages 31, a nice discussion about page 31, page 32, and page 33 to explain the idea of the sampling distribution, how we generate the sampling distribution, in this case for the sample mean. It's the same process, but I'm looking for a different statistics this time. What ends up happening is, and please watch those videos so you can understand this. I'm going to focus right now, because I have 40 minutes, I'm going to focus on using the results of the discussion in the videos. Here are the results. I'm going to start here. Oh, sorry. I'll just move it down. So, from sample to sample, there will be variability known as sampling variability. Okay, so even though your variable, I have to move it up a little bit, even though your variable comes from a distribution that's very regular, like a normal distribution in this case, with a specified expected value or mean, with a known standard deviation. If you take a sample and calculate a mean, so a sample mean, the first one that you calculate, the chance that that sample mean will be the same value as the population's mean. The chance that it's going to be the same is not 100%, okay? There's some variation. This is what this means. So it's one sample mean that came from a distribution of sample means that have the expected value of the mean, the population mean. So the mean of the variable was mu. So the means of the sample means, the expected value of the sample mean should be the same mean. Okay, so if you take a sample from a population, not every time will you get exactly the same average. So that it's clear though. However, if you keep on sampling, and take the averages from those samples, you should expect, and that's what this is saying, if you sample enough, you should expect to get on average the same mean as the population. So what is that talking about? So let's say I gave the example, probably I can't remember the video now, but maybe blood pressure. So when you get your blood pressure measured, now they have machines that will, while you're in triage or while you're waiting to see a doctor, they might measure your blood pressure not just once. They might take it with a machine. You can compute it, or you can take it 5 times, and then it will compute an average and report an average. All right. So because of the variation, because it's going to differ each time, it's more accurate to take the average of 5 than it is to just take 1. So that means that when we look at the distribution of the sample means, even though we pluck out one mean, let's say we pluck out a few values and get one mean, the distribution of means should be closer or more narrow around the actual mean. So there's less variation in the sample mean than there was in the original variable. So even though the means are the same, the expected values are the same, the variation is smaller, and not just smaller by a factor dividing by square root of n. So this is how precise the normal distribution is, that we, or the findings or the development of the normal distribution was such that the sample means who would have a variance in their distribution or standard deviation that was a factor smaller than the original variation or standard deviation. By dividing by square root of n, you'd have the new standard deviation. So this is how I'm going to refer to things as old and new, just like I did when I talked about the mean of, so we talked about the mean of the count variable, we talked about the mean of the sample proportion, and now we're going to talk about the mean of the sample mean. Sounds weird, but just hang in there. So this is the idea that the statistic has a distribution. Its mean is the same as the variable from which it was computed, and variable from which the observations were drawn to compute the sample mean. And the standard deviation is related, but it's smaller, and it's smaller by a factor 1 over square root of n. All right? So we're going to make use of that. Let's just apply that result. And I have the formulas here. So let's just apply that result here to this problem. Let x be a variable on some large population. Assume x is normally distributed with a mean and a standard deviation. So the variable of interest is known to be normal with a certain mean and a standard deviation already specified. And 1 minute. And let x bar be the sample mean. First, okay, and that's the sample mean calculated from a random sample of size 9. So that's my n, that's my mu, that's my sigma. Now we're going to create the new variable. This is the statistic x bar that has a distribution. And this is answer here is just to, I'm just answering the question, state the distribution. Well, it's also going to have the same shape. So that's one thing I didn't say back over here that I'd like to stress now. Do we expect the shape of the means, the distribution of the means, to be the same as the shape of the original variable? Yes, we do. All right, so this is a result of the rules of means and variances. If I'm just summing together variables that are normal, I'm going to get a normal back. Okay, and I do that proof on the subsequent page. I don't ask you to prove it. The intuition should be there, but if you need the proof, you can see the proof, and also it's a good exercise for practicing rules of means and variances to have a look at that. So the shapes will be the same, the shape being a normal distribution. Most of the observations are close to the mean, and then, well, around the mean, let's say it like that. And then a few observations are higher, an equal amount are lower, or equal distance lower. A few observations are much higher, and an equal amount are much lower and about the same distance away. Okay, so it's symmetric, bell-shaped, all of that. So let's answer this question. The sample mean will be from a distribution that's normal with the same mean, 13.8, but a standard deviation that's smaller. We're going to calculate it on the side here. The new standard deviation, and I use the symbol, the new standard deviation. Let me fix that up because it doesn't have to, like this. The new standard deviation is 2.9 divided by square root of n, which is 9. So allow me to give you a moment to punch that in your calculator and tell me what that is, okay? Nobody got the answer yet? The answer is very good, 0.97. Okay, so you put 97. I'm going to use my rule that I'm going to include 2 more decimal places than 2 more decimal places that were in the initial in the computations. So this would be 0.967. That's the number I would use. Okay, so I'll put it here, 0.967, and close the bracket. That's the answer. So now we have the distribution. So remember, all we're doing here, statistics is about means and relative measures. And what our goal is to estimate, right? Ultimately to alleviate uncertainty. So here's a distribution. I want to know, I've created the distribution or I derived it, and now I want to know, find the probability. So you're going to estimate what's the probability that X bar, so sample result, will be larger than 15. So the sample mean will be larger than 15. So how do I figure this out? Where's the distribution for X bar? Oh, I derived it above. Okay, so here it is. So I use this to standardize. So this is equal to X bar minus 13.8 divided by 0.967 gives me Z. Standardize. And what do you get? I'll give you a moment, make that calculation, okay? Very good, 1.241, very good, that's correct. But we're using the Z table, so we'll just drop the last place. So what ends up happening, even though I like to keep 2 more decimal places than were in the original values, because I'm going to use the Z table, I only need 2 decimal places. Alright, but to make the calculations, I'll keep 2 more than the original values, so we can get the same answers. That's the main point. You know what strategy I'm using for the decimals. Alright, so what would this answer be? Greater than 1.24. Make a graph, or make a curve. .24, 1 standard deviation, 0.24, and go right here To find this answer, you can go into the table and look up 1.24. That will give you the left side, and then you calculate 1 minus that. So why don't you do that? Look up in the table and give me this value on the left, the percentile. Oops. So the answer on the left side is 0.8925. So on the right side, it's 1 minus that, 1 minus 0.8925, or you could just look on the negative 1.25, negative 1.24 to get that answer. That's right, 10.75. So this is, the answer is 10.75%. Okay, so the chance of seeing more than 15 in the sample as a sample mean is it's small, it's 10.75%. If the original mean was 13.8, because the standard deviation is so small, it's going to be very tight distribution around the mean 13.8. So being at 15 is very unlikely. There's only a 10.75% chance of being 15 or more. Okay? All right, so I want you to try the second exercise on your own. I'll give you 3 minutes, and we'll regroup. So try that. Try not to look at the answers. All the answers are in these notes. Okay, that's why the notes are so thick, because I have questions and answers. Try not to look and see if you can do this on your own, and then I'll show you how to derive the answer. How's it going? Any questions? Okay, to solve this, we set it up. Okay, in the last problem, it introduced you to setting up to solve the problem. So to solve these problems with the sampling distribution, set it up. Begin by specifying what the distribution is so that you can then use it. So we want to set up the distribution. The weight of the eggs produced by a certain breed of hen is normally distributed with mean 65 and standard deviation 5. So that means X is, let's do this in black. X is distributed, so the original variable, actually let me move it over here. So X is distributed normally with a mean 65 and a standard deviation of 5. Think of cartons of such eggs as a simple random sample of size 12 from the population of all eggs. So now I'm going to take a sample of size n equals 12, and what is the probability that the weight of a carton falls between 750? So I want to know about the carton. So what I need to know about is the first, okay, from what I did above, what I'm going to get from here is the average, the distribution, sampling distribution of the sample mean. So this is the average weight of an egg in the carton. Okay, so this is also going to be the same normal with the same mean. Okay, so it's eggs but in a sample, and the standard deviation must change. So we have to find the new standard deviation using the formula. The formula said take the original standard deviation and divide by square root of n. So the original one was 5. I need to divide by square root of 12. And that will be my new standard deviation. So punching that in, that's 1.44. I didn't have any decimals, so I only have 2 here. So 1.44, so that's going to be 1.44. So we have the mean and standard deviation of the sample mean. The mean of the sample, okay? So it's the average weight of an egg in a carton. But the question asks, what's the probability that the weight of the whole carton falls between these numbers? Those numbers are much higher than the mean here, right? The mean here is just 65. So the approach I'm going to take is I want to use the information available to me. I want to use this information that I derived. So that means I need to change the question or frame the question so that I can adopt this information. The question has to be about the average weight of an egg in the carton, not the average weight of the carton. All right? So I'm going to change the question from 750. I'm going to try and keep the problem on the page here. So I'm going to take 750 and divide it by 12, and I'm going to take 825 and divide it by 12. because I really want the average in the carton, right? The average weight of an egg in the carton, which is, again, what I derived here. So once I do that, 750 divided by 12, this is 62.5, and the other one is 68.75. You see, those numbers are much closer, much more meaningful in the range of 65. Okay, so let's set up the problem. So it's really a matter of setting up these word problems. We want to find the probability that x bar, remember, we're using the new distribution, x bar is between 62.5 and 68.75. Does everybody have those numbers? So that's the question. To answer it, again, it's a matter of standardizing. I'm going to standardize. I'm going to subtract the mean and divide by the standard deviation. The new standard deviation, that turns that to a z. This is 68.75 minus 65 divided by the standard deviation. And I need to move that up. Simplify, make a graph, and answer the question. I'm just kind of waiting for you guys. Are you there? So if we look at my answers, right, the answers are going to be, so the answers are later, but I'll continue with solving. So this is negative 1.74. And this one is 2.60. So you have to then make a graph, use the normal distribution, and subtract bigger by smaller. Right? So 1.74 negative. .0409 and 2.6 is 0.9955. No, that's not right. It is 0.9953. And then you take big and you minus the small one to get the in between. And you find your answer. I'm just going to verify. So I get the answer as 95.44% when I subtract them. Can you see that? Okay. You take this one, subtract this one. And that is the answer. So that's pretty much it. Those are the kind of problems you're going to see for the situation where I give you information on a variable that is normal, and then I ask you about characteristics of outcomes for the sample mean that the sample was taken. Provided the distribution that you start with is normal, you can do this. So here, this was a normal distribution, so the sample mean would be normal. What if the distribution you start with is not normal? What do you do? This is the second result. In the second result, I take away the shape. I say I only have a mean and standard deviation of some population. And I don't know the shape of that distribution. I just know the mean and standard deviation. Should I be able to anticipate the same characteristics of the sample mean? In other words, can I arrive at this result about the sampling distribution of the sample mean if the original distribution was non-normal? In fact, in approximation, yes, you can, provided your sample size is large enough. And large enough, some textbooks use 30, some say 25. Just mathematically, using 25 makes calculations much more simple. So I'm going to stick with 25. But you get the point that it has to be a large sample, large enough sample. So 25 with a sample size of 25 or more will approximate the normal distribution as the shape, and arrive at the same results. The expected value should be the same as the original distribution, and the standard deviation should be smaller because we're more precise. We're going to get values in the sample mean of the sample mean that are going to be closer to the original or the true mean. So there's going to be some variability, but it's going to be less volatile than the original distribution. Okay, so what you got to do, you have to do the steps that we did before to solve these problems, but read carefully to be sure that you're told the distribution that you're working from is normal. If it's not normal, then check that the sample size is large enough, and you can continue as we did before, remembering your results are only an approximation. So you need to check So you need to check if it's normal, and then the N. Those are the things you're looking for. And then remember your result. If it's normal, then you just get the results here, right? You don't have to worry about anything special. If it's not normal, just look at the sample size to get the same results in approximation. Okay, so it's 6 o'clock. I'm going to encourage you to work through these problems, these exercises, until Monday. Do some problems, read through the notes. There's so many exercises. Try them, sketch out your answers, and check you're doing it right. There's the answers. There's more problems, solutions. Oh, and then we arrive here. Now there's a video for this. Watch this video, okay? And as far as I'm concerned, I have presented you Unit 5. So Monday I could actually start Unit 6, but I'll probably leave Monday for answering questions. So send me your problems, send me your questions for Monday, Tuesday, Wednesday, and what I'll do is I'll spend half the time maybe solving problems and the other half introducing inference. So we'll have about 2 weeks to discuss inference and do problems, and I think the last day of class should be the 15th of May. I have to check if they actually finally changed the calendar. And then I'll set up a day for the final exam. It's going to be on a class day, so in terms of your schedules, always keep your Thursday nights for stats. Okay, have a good weekend. Be in touch about problems you want me to solve. Take care.